We can further refine our model for colligative properties by using the vantov factor. So it's described, the vantov factor I is going to just get thrown in there in the beginning. And your equation, instead of becoming delta t is equal to k times m, it's delta t is equal to I times m times k, or kim, or mik, depending on which particular celebrity you're more fond of. K represents the freezing point or boiling point depression constant. For osmotic pressure, same idea, you just throw in this I term at the beginning. So the relationship between the molecules of solvent and the number of moles and the moles of the particles in solution is usually expressed using the vantov factor I. And like I said, it's real simple. How many moles of particles do you get out? Divided by the moles of solute dissolved. So something like calcium chloride, which is going to dissociate into calcium 2 plus and 2 Cl minuses. We have 1 plus 2, that is 3. So its vantov factor would be 3. Right? The expected value for I can be determined for a salt by noting the number of ions per formula unit. Calculated values assume complete dissociation and free movement of ions when a salt is dissolved, but ion pairing occurs in solution, leading to a little bit of a deviation. So we refine our model by using the vantov factor. We then look at ion pairing and refine that initial guess a little bit more. Deviation from I from the expected values tends to be greatest where the ions have multiple charges. So your calcium 2 plus, multiple charges, going to be a little bit more of a deviation than something that would be like, I can't think of a good example where it's going to have 3 things that dissociate from, that are only going to have single charges. And that's, again, this is an electrostatic interaction, right? So we've seen Coulomb's law show up again and again and again and again, right? It's kind of underpinning a lot of what's happening here, where energy is related to our charges and how far apart they are. Right? So it's more important for highly charged ions. So for a given instant, a small percentage of the sodium and chloride ions are paired, right? They see each other in solution. They're like, oh, hey, you're plus charge. Oh, hey, you're minus charge. Want to hang out, and then they remember, oh, wait, we're dissolved in water. Right? So this ion pairing is most important in concentrated solutions. The higher the concentration, the bigger the deviation. The larger the charge, the bigger the deviation. As the solution becomes more dilute, the ions are further apart, the less of this pairing happens, the closer it is to that ideal I value. Right, so when you look at these I values, so sodium chloride is going to break up into 2 things, right? Na plus and Cl minus. All right, so you're expecting 2, and it's pretty darn close to that. The vantov factor would be 1.9. For something like magnesium chloride, where you've got that Mg2 plus, it's going to, you expect it to dissolve into 3. You'd expect 3, it's a little bit less. And so you notice that all these things are a little bit less because that ion pairing makes them want to act like one thing and not 2 things. Glucose, which is a non-electrolyte, right, doesn't dissociate into ions. There's no force of attraction because there's no Q involved in that, no charge. So HCl, pretty close to ideal. All right, so the larger your charge, the more of a deviation you get. Right? The higher the concentration, the more deviation you get. And we'll go into this a lot more in analytical chemistry if you take that with me later on, or you take it with somebody else, but you'll cover that in analytical. So let's look at an example. The observed osmotic pressure for a 0.1 molar solution of iron ammonium sulfate at 25 degrees C is 10.8 atmospheres. We're going to compare that to the experimental values for I. Right, so this is what we measured, and this is what we're going to figure out what it should be in theory. So our ionic solid, FAS, iron ammonium sulfate, so FAS, where this is ammonium and sulfate, dissociates in water to produce 5 ions. So you're going to take this FAS, you're going to dissociate into iron, 2 ammonias and 2 sulfates, so 1 plus 2 plus 2 is 5. We expect the I value to be 5. Right? We can obtain the experimental value for I by using the equation for osmotic pressure. Pi is equal to I times mRT. Rearrange it and do I is equal to pi over mRT. We said that our pressure was 10.8 atmospheres. Our molarity was 0.1 moles per liter. R is 0.0821 liters atmospheres moles Kelvin. And we're going to do 298 K. So we know pi, we know M, we know R, we know T. We can solve for I. So 10.8 atmospheres divided by 0.1 moles per liter divided by 0.0821 liters atmosphere mole Kelvin. Atmospheres drop off. Right. Kelvin drops off with that Kelvin. Notice this is unitless. And we end up with 4.4, which is less than 5. So experimentally, we'd expect 5. We measured it, we get 4. All right. Our last part of chapter 10 is our section on colloids. This is near and dear to my heart. I worked with a lot of colloids when I was in grad school. The nanomaterials that I make, there are gold colloids and silver colloids, and so a little bit of semiconductors. So a suspension of a tiny particles in some medium is also called a colloidal dispersion. Now these are not dissolved, they're just kind of floating there. So if you've ever seen like dust in a sunbeam, like that is what it's like. It's not like where the oxygen and the carbon dioxide are dissolved in the air. It's something that's kind of floating around in there. They're never going to settle out. Right? They're never going to precipitate down at the bottom. They're suspended. They are single large molecules or aggregates of molecules or ions. They're going to range in size between between 1 and 1,000 nanometers. So they're really small, and some of them could be a little bit bigger. You have probably seen the Tyndall effect. So this is light scattering of particles that are in this kind of suspension. So that's when you see that sunbeam, or those, like, I think they're called God rays, and you're like, psh, there's that beam of light that's coming from a cloudy day and it's hitting some of those little rain droplets or dust in the air. Or if you see the beam of a flashlight in a dusty room, that's the Tyndall effect. It helps distinguish between a suspension with colloids and a true solution where those molecules are completely surrounded by the solvent and undergo that kind of solvent-solute interaction. They're classified according to the states of the dispersed phase and the dispersing medium. So again, similar to solute and solvent, you've got fog, aerosols, or sprays where a gas is the dispersing medium and you have a liquid that is suspended in them. And we call that an aerosol. You could have a gas with a solid dispersed in it. It's also called an aerosol. So smoke, airborne bacteria. You could have a gas dissolved in a liquid, and that's called a foam. So whipped cream, soap suds. You can have a liquid in a liquid. So fat, which is not soluble in water, and water is going to be something like milk or mayonnaise, right? That's why you have to homogenize the milk so that it doesn't separate out the cream, which is fatty and non-polar, from the rest of the milk, which is mostly water and polar. That's called an emulsion. You could have a sol, S-O-L, where a solid is dispersed in a liquid. So paint, clays, gelatin, the nanomaterials I work with, those were sols. You could have a solid foam where a gas is dissolved in a solid. Right? So polystyrene foam, that fill foam, marshmallow. You could have a liquid dissolved in a solid. Right? So it's called a solid emulsion. So cheese or butter are going to be solid emulsions. Or you could have a solid in a solid. It's called a solid sol. And something like ruby glass would be a solid sol. When particles of colloids are placed in an electric field, the dispersed particles all migrate to the same electrode and then all have to have the same charge. The center of colloidal particles attract from the medium a layer of ions of the same charge. This group of ions attracts another layer of oppositely charged ions. So these guys are going to float around, and oftentimes they'll have like a layer of plus charges or minus charges on their surface. Right? And so when they do that, they can attract a second layer of minus charges around them. Right? Since the particles all have an outer layer of ions with the same charge, right? Here's another one, right? It's got some plus charges on the inner layer, right? And some minus charges on the outer layer, right? Well, these outer minus charges and these outer minus charges want nothing to do with each other, so they repel each other. So they're kind of playing bumper cars. It's like, whoop, nope, don't want to be around you. Since the particles all have an outer layer of ions with the same charge, they repel each other and do not aggregate to form larger particles that are going to be big enough to precipitate. You can kind of force these things to coagulate, so it's the destruction of a colloid. So you can either heat them or add another electrolyte. So remember, this guy's got a minus charge around its surface, basically. That's repelling it from a minus charge around this one. If I throw in an electrolyte, throw in some plus charges, well, that plus charge can act like a bridge. And now this particle is attracted to the plus charge, and this particle is attracted to this plus charge, and maybe they accidentally touch, and then they form a larger solid and precipitate. Heating basically says, okay, this guy in the middle is going to move so fast that those solvating ions just can't keep up. Right? The ions are moving so fast they either bump into each other, or the minus charges and the plus charges can't keep up, and they get removed. This process gets repeated many times. The particle grows and grows and grows to a point where the random motion can't keep it suspended anymore, and it's going to precipitate out. Adding an electrolyte helps neutralize that layer of absorbed ions. For example, in the removal of soot from smoke. So Cottrell precipitator installed in a smokestack. You've got an electrical charge basically that you're putting onto it. So this guy is grounded. You've got some plate electrodes up here and some individual point electrodes. Right? As your soot-laden smoke, which is a colloidal suspension, goes in across these electrodes, those are going to act like an electrolyte would. It's going to remove some of those charges or cause that oppositely charged particle to be attracted to these point electrodes. And so those soot particles get removed down out the bottom, and then the soot-free gases are free to escape. They were really popular in home, like as ionizing filters for quite a while, and like Sharper Image sold a bunch of these guys. All right. And that's the end of chapter 10 for us. We'll pick it up again with chapter 11. Thank you, guys.